Okay, thank you for the introduction, Rich. And I'd also like to thank Park Systems and NanoScientific for giving me the opportunity to come here and talk about some of the work that we've done in the semiconductor industry. The industry itself has been undergoing rapid evolution over the past few years. And because of this evolution that we're going through, it's necessitated the requirement to come up with analytical techniques that are going to support the latest technologies, everywhere from technology development, to finished products. We need to be able to understand the functionality, and as a consequence, we've had to develop new techniques for analysis, and scanning probe microscopy has lent itself very well to giving us an understanding of these new devices. One of the biggest transformations that the industry has seen in the past few years is going from two-dimensional devices, planar FETs, to the three-dimensional FinFET structure, state of the art. Ji-Young just gave a nice talk about the bipolar junction transistors. Well, I'm going in the other direction. My talk is going to be focused around field effect transistors and the evolutionary process in how we analyze them. Specifically, the analytical technique that I'm going to talk about is called scanning capacitance spectroscopy. It's a technique that is related very closely to scanning capacitance microscopy, but what it does is it takes it a step further and enables us to understand much more about devices from the two-dimensional structures to the state-of-the-art three-dimensional FinFETs. So, the first thing that I'm going to talk about, I'm just going to give an overview of semiconductor devices. Again, Ji-Young talked about the bipolar junction transistors, and I'm going to talk about two-dimensional devices, regular planar FETs, which has been, the planar FETs have been in existence for probably the last 40 years. I mean, that's been the basic fundamental building block for semiconductor devices for 40 years now. Lately, we've converted over to three-dimensional devices. The motivation for the industry is to make devices smaller, faster, and more efficient. So the two-dimensional device, eventually, they kept getting smaller and smaller and smaller. Well, something had to change. So the transition to three-dimensional FinFETs, we're going to talk a little bit about FinFETs, the structure, the functionality. I'm going to talk a little bit about scanning probe microscopy techniques, the techniques that we've used over the years to analyze these devices, to be able to provide empirical data to device designers, technology developers. They design and build these structures, but what do they really look like? Okay, so we've used a number of these techniques to give that information back to technology developers so that technologies can evolve faster and much more accurately. I'm going to talk about scanning capacitance microscopy. I'm going to lump these two together, scanning capacitance microscopy and scanning capacitance spectroscopy. Again, the spectroscopy portion of it is taking SCM one step further to give us that much more information. And then I'm going to go forward with a couple of case studies where we used scanning capacitance spectroscopy to understand what was going on in an individual device, an individual planar FET, two-dimensional device. And then we're going to talk about how we're using scanning capacitance spectroscopy to give us data on the latest technology, the 14-nanometer FinFETs. And then I'll finish up with just some concluding remarks. So let's talk about semiconductor devices from 2D to 3D. I mean, this is a slide that I'd like to use all the time. It gives you a fundamental understanding of how the two-dimensional FET is constructed. You need to have a good understanding of that to basically get an idea of why we're so interested in some of some of the components that build up this structure. So essentially, we're going to go through just a quick overview of the fabrication process. And basically, we start by defining areas in silicon where the devices are going to be built. We have two different types. We have a p-channel device and an n-channel device. Basically, just one switches on a positive signal and one switches on a negative signal. That's all in a simplistic fashion. And what we're going to do to fabricate our n-channel devices, they're going to go in a p-well, and our p devices are going to go in an n-well. Next thing we do is we put down a thin gate oxide, okay, because we want this polysilicon electrode to excuse me, to be insulated from the surface. So when we apply a field here, we're basically just going to switch this device on and off. And again, I'm moving quickly through this, but here's the important part. When we start doing these implants, to actually define the device, define the functionality of the device. So for our N-channel device, I mean, we're sitting in P-type silicon, and we're going to implant arsenic and phosphorus over here. And conversely, for our P-channel device, we're sitting in boron-doped silicon and, arsenic and phosphorus-doped silicon, and then we're going to put boron in there such that we have on one polarity device NPN and the other PNP. And then in order to turn the device on and off, basically we're just going to apply a charge on the polysilicon gate there and essentially turn one switch on and one switch off. So, but the important thing to know, to take from this, is the fact that we're very, very interested in these dopants and how they distribute themselves down in the silicon, because that has a significant impact on how the device is going to operate. And if those implants aren't put in there properly or they haven't diffused properly, we're going to have a malfunctioning device. Okay? And when you're putting 10,000, 100,000, a million of these on a single piece of silicon, and you've got one of these that is just a little bit off, that makes the whole device non-functional. Here's where we're at now, state of the art, the FinFET, the three-dimensional device. Essentially the same operating principle. We'll have N, and then in here P, and then N. So we're gating this device on and off the same way that we do with the two-dimensional structure. It's just now we've got this fin with the gate wrapped around it. Hence the three-dimensional structure. So essentially what we would do is put a charge on this gate, which would, say we've got an N-channel FinFET. So we're doped with arsenic and phosphorus out here in the source and drain. That's N-type. And under here in the gate region, it's doped with boron, making it P-type. And we put a charge on here that inverts that P-type to N-type, turning this device on. So we can make these devices incredibly small. I mean, right now, current production technology is at 14 nanometers, with the next phase of production technology going to 7 nanometer. So that's our three-dimensional FinFET. Now, let's talk a little bit about some of the SPM techniques that we use for nanoscale semiconductor device analysis. We use a whole host of various techniques to analyze semiconductors. I mean, basically, every analysis, there's some level of atomic force microscopy because of its ability to resolve very, very small features. And we also use scanning Kelvin probe microscopy to look at work function and charge-related phenomena. And then, of course, scanning capacitance microscopy, which I'm going to get into in a little bit more detail for dopant analysis. I mentioned how critical it is for dopants to be in the right place to have a properly functioning device. And scanning capacitance microscopy has been the workhorse technique that has given us the capability to analyze devices from the micron scale many years ago down to the nanoscale devices that we're at now. The spectroscopy technique is what I'm going to talk about in detail, and how that's enabled us to get much more information out of the device rather than just taking a simple scanning capacitance microscopy image. We use conductive AFM for looking at dielectrics. As devices continued to shrink and shrink, the dielectrics kept getting thinner and thinner and thinner, such that a single molecular contaminant, a single molecule in the wrong place, would render a device malfunctional, anomalous, and could render a whole chip basically useless. So we've used conductive AFM to analyze gate dielectrics, the thin dielectrics, and get a very accurate representation of the overall dielectric integrity. Magnetic force microscopy for looking at conductors, looking at magnetic fields around conductors, looking for anomalies in conductors that you may not be able to see. They may be subsurface. We developed a method for looking for subsurface anomalies in conductors. And then lastly, scanning surface photovoltage microscopy, just another technique by which we can get an idea of what the stress levels are in silicon, because one of the evolutionary steps in semiconductor technology was strained silicon, either adding compressive or tensile stress on devices to enhance mobility. So this is what we're focusing on today, SCM and scanning capacitance spectroscopy. So let's talk about scanning capacitance microscopy. It's a dynamic technique in which an image is created representative of the capacitance between the probe and the sample. Whereby electrically active dopants, so we're getting an image, we're collecting data based on the electrically active dopants in a semiconducting material. And essentially the way that we're doing it, we're sensing the depletion capacitance. So if we look up here, okay, this is an example that I've got showing P-type silicon. So we've got all this positive charge here, and then separated by a dielectric, which when in analytical lab will grow with a thin dielectric on there. And here's our SPM tip right here. So it's a conductive tip. Let's say we connect them all electrically. And essentially what we've got here is a capacitor. Now, if we are to take and change the bias conditions, what we can do is we can pull that charge away from the surface. So what we've done here is we've put a negative charge in the bulk silicon, and we've pulled that P charge, the holes, away from the surface. We've essentially moved one plate of that capacitor away. And what happens is this D increases and the capacitance goes down. Essentially, that's how the technique works. It's very simple. So how do we determine whether or not we're looking at N-type or P-type silicon? We do a dynamic measurement. So we put a small AC signal on there, which gives us, we move back and forth across the CV curve. And what happens is as we're transitioning on this CV curve, we're recording the slope of that curve. And based on the phase and the magnitude of the data that we get back, that tells us if we're looking at N-type silicon or P-type silicon and the relative concentration. Typical concentration range is about 10 to the 16th to 10 to the 21 impurities per cubic centimeter. And the tips that we're using now, they're silicided silicon tips. So in other words, it's a conventional silicon tip onto which a metal has been deposited. Then you anneal it to create a silicide. Silicide is conductive, and it's strong, and it retains the sharpness of the tip. So some of the highest resolution work now is done with silicided silicon tips. So that's scanning capacitance microscopy. So here's the spectroscopy portion of it. What we do, if you look at the CV curves here, for a highly doped silicon, it kind of flattens out. And what happens is we start to lose our contrast because the slope here is getting shallower and shallower, and eventually this line would flatten right out and we get no signal at all. So our best dynamic range is where we get a large change in capacitance for some given change in voltage. Our DC dV is at its peak. So what we do in order to perform the spectroscopy is we'll put a number of different DC biases on the sample, basically to change the state at which it's starting. Okay, so if we've got very heavily doped silicon, we'll put a bias on there that's going to pull some carriers away from the surface, and that will leave just a few carriers left, and we can then manipulate them with this AC signal that we're putting on there. Okay, so what it does is it gives us the ability to see things which may not otherwise be detected just using straight scanning capacitance microscopy. Just a little bit a different way to represent what we're doing here. Let's look at a silicon sample with a moderate concentration, say maybe 10 to the 17th atoms per centimeter cube. So we've got N-type silicon, so we've got electrons sitting at the surface, and what I've drawn is a plate here, and that plate would essentially be our AFM tip, separated by an oxide. So here, sitting at 0 volt DC and 0 volt AC bias, okay, we have a capacitor. We have some level of capacitance, but it's not changing. It's going to be static. So the derivative of that CV curve is going to be 0 because it's static. Now, let's take the same sample and let's put a small AC bias on it. So what's going to happen is those electrons are going to move away from the surface and come back to the surface and just continually keep going back and forth. So what we're doing is we're effectively moving one plate of that capacitor. It moves down and back up, down and back up. And what we'll do is we'll look at the slope. We'll look at the slope of that CV curve. Now it's non-zero. So now we're going to see what's actually going on here. Okay, that's in the case of a moderately doped sample. Now, let's look at the situation where we've got a high concentration. So we've got a heavily doped N-type silicon. So now we've got a much higher concentration here at the surface. And again, in a static condition, we've got our capacitor. We don't really see anything. Now, let's put our little small signal AC on there. Okay? Well, we've got enough potential to move some of the carriers, some of the electrons away, but not quite enough to move all of them away. So as a consequence, that plate does not move because we cannot move all of these electrons away from the surface. So therefore, this representing heavily doped silicon, we're not moving that plate of the capacitor. We don't get any signal. So here's the solution. Let's put a DC bias on the sample. Okay, so what we do is now, in this case, we're putting a positive bias up through the substrate. We're going to pull some of those electrons away from the surface. So we've got a high concentration. We're going to pull some of the electrons away from the surface, leaving these guys up here. Well, again, in a static condition, we don't see anything. But now, when we apply that small AC bias on top of the DC, what happens is we now start to move the leftover electrons away from the surface. We move them away, they go back. And now, that enables us, in a situation where we've got heavily doped silicon, to get a signal. So now we're moving that plate, we're getting a signal. Okay, so this is a situation where we have highly doped silicon that enables us to get an image where we otherwise wouldn't be able to do that. In spectroscopy, what we do is we take it through a whole series of different bias conditions to look at low doped areas, because if we flip this around, we can force low doped areas into accumulation. That's the converse of this. So that enables us, by using a series of different bias conditions, to start to pull data out where we've got really low doped silicon or very heavily doped silicon where we otherwise would not be able to get a signal. So that's essentially what we're doing with scanning capacitance spectroscopy. Let's look at a couple of case studies. I'm going to give a couple examples, one on a planar device and one on a three-dimensional FinFET. So just a little bit of background for the first example I'm going to talk about here. And actually, it's pretty amazing what these devices go through in an analytical lab, especially in a situation where there's failure analysis. I mean, the device will be taken from, say, fully packaged and systematically delayered, layer by layer by layer, to get an understanding of where an anomaly or where a failure mechanism may exist. And again, they'll start at a fully packaged chip and take it all the way down. And when it gets into my lab, we dissect an individual FET, because it will be systematically narrowed down using scanning electron microscopy, electrical isolation, photon techniques, until we get down to the area of interest. And if it gets down to an individual device, the guys in my lab will take that FET apart and understand why that individual FET was not working properly. So in this particular instance, we had 3 NFETs, and they had progressively lower levels of I-off. Now, what I mean by that is when that device was turned off, when those devices were turned off, you want them to be off. You don't want any current flowing through them, because if there's still current flowing through them, what's going to happen is you take a handheld device, and the battery's going to run dead, but it's doing nothing. It's just doing nothing but wasting current. So you really want when these devices are off, they're supposed to be off. So we had a few devices that were singled out that were still showing signs of current flow when they were supposed to be turned off. This is the design data, basically showing what the devices were, and here we are, N1, N2, and N3. There were 3 N-channel FETs that were leaking, all in the same location. So what we decided to do is we were going to look at these cross-sectionally using scanning capacitance microscopy. So here is the dopant profiles of N1, N2, and N3. What we're looking at over here is a topographical image. And one of the requirements that we have when we're going to do good scanning capacitance microscopy is that this surface here has to be absolutely smooth as we can possibly get it. Kind of the requirement that I've placed on it is RMS roughness of less than 5 angstroms. So I mean, we're looking at something that's virtually atomically smooth. And we've developed techniques by which we can accomplish that. If you don't have a smooth surface like that, that can convolve artifacts into your data. So what we're looking at here is the 3 devices, and this is where the polysilicon gate was. And I'm showing the little image up here. So here's our polysilicon gate, and then the doped regions would be here. So N1, N2, and N3. And over here, these are the dopant. This is the dopant profile of those 3 devices. Now, when I look at that, let's take a look. So this right here, our source and drain diffusions are right here for each respective device. And I mentioned the fact that a very heavily doped silicon is not going to show up. Well, sure enough, I mean, right here in the source and drain areas, they're doped N+. That's why we don't see anything there. But if you look at these devices closely, right in here, we're going to have a p-type channel. And so let's look at this device over here. Now, this was N3. And you can see some semblance of a channel right there. You can just see where it transitions from N-type to p-type. But as we go to N2, it gets a little bit narrower. And N1, one would argue whether or not there's actually a channel there. It's kind of closed right off. So, that kind of gave us a clue of what to look for. Because a device like this, it's going to leak. It's going to pass current when it's turned off. But just looking at this one data point, if you will, it wasn't really conclusive. So we performed scanning capacitance spectroscopy on these devices, in which, we applied a series of different DC bias conditions. And right here's our 0-volt image. So that's the same image that we just looked at on the other page. And again, we see that same phenomena. Let's go over here first. We applied -1 volt up through the substrate. So what that does is that causes the p-type silicon in the channel to invert. And sure enough, all 3 devices, the p-type silicon inverted. So this is the same thing that would happen when you turn the device on. Okay, we've got N+, we've got N+, the device is turned on. So that was good. I mean, that showed us that those devices would function properly from a dopant standpoint. Now let's go the other direction. So let's look at +1 volt bias. So we've applied a positive +1 volt up through the substrate. And now we're going to start to force that channel into accumulation and eventually saturation. And now you can see we've got some changes going on here. First off is these source and drain diffusions are starting to go away. They're starting to deplete. Okay? And we can also see some changes in the channel. And it becomes really evident over here when we go to 1.5 volt DC. You can see there's clearly a difference between N1, N2, and N3. And essentially what that has told us is over here, N3 has gone into the steep slope of the DC-dV curve, the CV curve, and it's becoming bright. It's more white than the other 2. And essentially what that tells us is the concentration, the channel concentration is highest here, and it's lower there, and it's lower there. Okay, so essentially the spectroscopy confirmed what we had suspected, that the boron concentration in the channel of those devices as we went from one to the other was getting progressively less, thereby explaining from a dopant standpoint why these devices leaked. And this just happened to be 3 devices on a chip that had it was hundreds of thousands of FETs. These 3 were, well, actually, this one was okay, but these 2 guys were non-functional or malfunctioning. They worked okay, but they just leaked. So that's just a restatement of what I just said. We basically, using the spectroscopic analysis, we were able to understand the cause for the malfunctioning of those devices. Now, let's look at another case study. This is in a 3-dimensional device fabricated 14-nanometer FinFET technology, state-of-the-art production. And in this particular analysis, we're looking at the same problem, off current. I mean, the device is turned off, but it's still leaking current. The challenge with this was to perform scanning capacitance microscopy on a single fin, a single called-out fin, because the sample preparation, in order to get to one fin on a device and have it in a state that you can analyze it, is incredibly time-consuming, tedious, and difficult. And we had one chance, because if we miss the device, the analysis is over. So we decided to use a cross-sectional approach. We had most experience with that, and we decided that would give us the best chance for success. A little bit more background, and I won't get into too much detail here other than some electrical testing. And this is kind of a testament to some of the work and testing that's done to localize these devices. So this device eventually got localized to a circuit, and then it went into an SEM with probes, and they went down and they actually go in and probe the individual structures and come up with the electrical characteristics. So this is what we got here. This device, when it's turned off, ideally we would want to see very low level of leakage, 100 picoamps or less through that device. And in one direction, in the forward bias direction, we were getting approximately 2.4 nanoamps, and then swapping it around because these devices are all symmetric. They should exhibit symmetry. But when we swap the source and drain around, we got an order of magnitude more current passing through that device. So that gave us a clue that the problem with this device is probably biased towards one side. So that kind of helped us with what we decided to do when we prepared the sample. So essentially, what we did was we decided to polish into this device using just some procedures that we've developed over the years in looking at two-dimensional planar devices. This is a TEM showing the view that we wanted to get. Here's our fins. And I mean, we need to look at this area here. Okay, that area there is 26 atoms across. Actually, the device. The device is 26 atoms this way and 26 atoms this way. So it's not really drawn to scale here. But that's the area that we're trying to hit. And another thing. Okay, we need to maintain sample integrity. Focused ion beam techniques are very, very accurate in getting to areas. And there's a lot of FIB used in sample prep now. But the problem with using FIB is that it creates an amorphous layer based on the accelerating voltage in the FIB. And that amorphous layer at 5 keV is about 10 nanometers, and it ranges up to about 30 nanometers at 25 keV. Well, even at 5 keV with a 10 nanometer amorphous layer, our interaction volume is much less than that, so we don't get a signal. So we couldn't use any focused ion beam techniques to prep the sample. So we had to resort to our traditional brute force method of grinding away silicon and then slowing down the polish as we approach the device. And this is a testimonial to my colleagues who actually prepped this sample, to their skill and patience in doing this. And I'll show you why in a second. How do we know we're at the region of interest? We can't see these things. They're so small, you can't see them. We can't put them in an SEM. Not when we get close to the area of interest, because that's going to put carbon on the sample. It's going to damage the sample. We can't do that. So we're limited into how we're going to navigate to right there, the area of interest. What we did was we put some navigation marks in here using focused ion beam, and we're polishing from this direction, coming in this way. And then we put some X's here. So we know when we're starting to get close to the area, and this SEM cross-section right here shows that we're right about here, because we can see our center mark, and we're just starting to get into these two marks. And then when we get further and further, when we start to see these X's, as those X's converge, when we're looking at this cross-sectionally, just using optical microscopy, and then as we got closer and closer to the device, we'd actually put it in the AFM to get a topographic image to know when we're getting close. But that would tell us when we're getting close to the area of interest, and we need to really slow down our polishing. Sample prep, it gets complicated with these because we're trying to hit such a small target and not have it damaged. So essentially what we did, in order to make electrical contact, because we have to make good electrical contact to all areas of the device to get a good signal. So as the sample came to us, because they had delayered it for probing, the contact levels were exposed. So let's make use of that. What we did was we put 300 angstroms of chromium over the whole surface. So now all of the contacts that actually go down to the device, are all connected with this plate of chromium that we've put on top. And that plate extends out to the edge of the chip, and we'll eventually make contact to that using silver paint. And then just for structural integrity, we put a thin layer of epoxy and a cover glass on top of it, because we're going to be hand polishing to minimize the effects of polishing in terms of rounding and just kind of holding everything together. But again, this is the view that we want to get. When we got close to the area of interest, like I mentioned, we had to really slow down our rate of polishing. So what we did, we got to a certain point, when we got within a few nanometers of the area of interest, we switched over to hand polishing. Everything done up to this point was done on a machine that with the pattern recognition that would get us close to the area of interest. But as soon as we got here, as soon as we got to where we could see that contact, it's time to start hand polishing. And the way that we did that, this is on a home-built fixture that we made, that the sample gets mounted. You know, you can see a sample affixed to the end of it right here with some micrometers just to position it. Pretty straightforward. We used a 0.04 micron silica slurry on a pad, absolutely clean pad. And essentially, we took that fixture and set it on the pad with the slurry, did a figure 8, and then removed it. Cleaned it into the AFM, and repeat. So back and forth, back and forth, back and forth. And this went on for, well, a few weeks. Because really, I mean, you know, we're trying to remove atom by atom. And we don't want to overshoot our target. So, you know, this is where I said, I mean, this was a testimonial to the skill and patience of my colleagues who prepped this sample, because it was a very long, tedious effort to do it. But they were successful. What we're looking at here is the dopant profile of those the two adjacent devices. And this was the one that was problematic right here. And you can see, here's our fins, N-type silicon, because it's a PFET. And if you look at our NFET, looks perfect. Right there, I mean, there's clearly a defect in that one fin, this tiny spot. So, I mean, we know we've got a localized defect, but that's all we know. Because if that area happened to be a lower concentration than the surrounding area, that's not a problem. If it's got a higher concentration than the surrounding area, it is a problem. So how are we going to figure that out? We switch over to scanning capacitance spectroscopy. So here's a spectrum. Here's a spectrum of what we did on that device. So here's our 0 volts image, and here's our defect. And then what we do is, as we progress through different bias conditions, let's look and see what happens to that defect as compared to the surrounding area. And what you can see, going from 0, as we progress in a positive direction, we can see that defect is still there, but the surrounding area is starting to disappear. The surrounding area has disappeared, and our defect is still there. Or some evidence of the defect is still there. So that told us conclusively that area had a higher concentration of arsenic and phosphorus than the surrounding area. So essentially, that's what we were out to get. That's what we were out to get in this analysis, finding the root cause and the explanation for the fact that this device would leak, because we've got a high concentration of arsenic and phosphorus there that is providing a leakage path. Now, one of the other things that we get out of this is, if you happen to look, okay, when we go in this direction, so we're applying a positive bias, our PFETs are actually, if you look, I mean, we see it starting to the channels starting to disappear here, and but now they're starting to invert as we progress through the different bias conditions. This is the same thing that's going to happen when that fin is turned on. So what we've done is we've artificially put that channel into depletion and eventually inversion. And then going the other direction, if we look at the NFET, sure enough, over here, starting to invert, and now we've got the channel inverted on the corresponding NFETs. And that's another tool that one can use to understand if a device is operating as expected, as hoped. So just another benefit of this spectroscopic technique. So essentially, the results of that analysis showed that 2 of the 3 fins were normal, and the presence of a local defect in the rightmost fin of P4, our suspect device. And it also showed that conclusively that area was a higher end concentration. And what I'm showing here is basically a simplified schematic of what those 2 devices looked like. In this case, we're looking at a good functioning device, because we've got P-type, N-type, and P-type, so we've got 2 diodes basically pointing at each other. So it shouldn't leak in either way, because in any case you're going to have a reverse bias diode. But this is what we had. This is the equivalent circuit representing what we had on that anomalous device. Okay, over here we had no diode. Over on the source side we had no diode. And over on the drain side, that diode was partially compromised by the incursion of the arsenic and phosphorus over on one side. So as a result, in one direction, when this thing is forward biased, we're going to have high leakage, okay, because we've only got this weak diode to prevent current from passing through. When we swap the leads around, or we swap the bias conditions around on the device, we have very high leakage, because now this device is forward biased and we have nothing to block it over on this side. So that essentially corroborated the electrical results that led us to this particular device. So in conclusion, I'd like to say that dopant analysis on even our most advanced technologies is possible. I had a gentleman at a recent conference tell me that it wasn't. And I just happened to have my laptop with me, and I showed him, well, I think it is. And this is at 14 nanometer, and I think we can still get to 7 nanometer, but I mean, there's certainly room for development in SPM, scanning capacitance, to enable us to get to the next technology node. And also, scanning capacitance spectroscopy, it's a powerful technique. It's proven to be a powerful technique for identifying relative concentration and localized anomalies. And it doesn't really take that much longer. That particular series of images that we took us a little over an hour. Because once we're localized in on the area of interest, we just keep scanning and changing the bias conditions. So it's not really that major of an investment in time. But the one thing is precise sample preparation is necessary for successful analysis, especially at these technology nodes. And again, thank you for the opportunity to share my work with you.
Questions?
Yes?
So how do statistics on problems like this, and then how you integrate this in the workflow? Because you can't do this, right, for every problem.
Right, yep.
So you figure out what the signature is of a kind of problem?
Yeah. So the question is, statistically, I mean, how does this integrate, into the manufacturing process? And here, we've got one data point. Okay, so essentially, this data would be taken forward and just hung on to. If you start seeing a pattern, then you start looking back into, was this device, were they all made on a specific tool? Maybe a specific ion implanter or litho tool. Is there some pattern that where we can trace back where this is happening? The other thing is, could there be some pattern-related problem in the layout of the device? And again, you may, on one data point, you may take a quick look at it because it's no really, you're not digging too deeply into a manufacturing process, but you can look and say, well, okay, this might be something I may need to keep an eye on because, and this is especially problematic with rapid thermal processing now, where your anneals, taking up to hundreds and close to 1,000 degrees C happens just over a few minutes rather than hours. Rapid thermal processing tends to cause defects in silicon because of thermal gradients. And a defect in the silicon created by that might be an area that's going to accumulate dopants and build a conductor subsurface that facilitates something like this. So depending on the fail signature, you may wait until you have built up a database to take action, but then other fail signatures may warrant immediate action. Yes? Oh.
Okay, I was wondering if you ever changed the frequency of your signal to maybe estimate carrier mobility or something else?
Great question. And so the question is, do we ever modulate our stimulus frequency, to look at carrier lifetimes? And one of the other techniques that I showed up, there's the scanning surface photovoltage microscope. Actually, what we're doing is we're experimenting with illumination with laser light and carrier lifetimes. So for this particular technique, essentially what we do is we find a frequency that's kind of the sweet spot for giving us the best signal-to-noise ratio, and we go with that. But there are other projects going on where we actually we published our results, where we were actually able to extract a carrier lifetime using scanning surface photovoltage microscopy.
You mentioned you can tell the defect site has higher electron concentration or higher n-type, whatever. My question is can you tell the absolute concentration or just relative?
Okay. So the question is, what I showed, we're able to get a relative concentration. Comparing in this particular instance the defect site with the area around it. The question is, can we come up with the absolute concentration? The answer is no. That has been the holy grail ever since scanning capacitance microscopy first evolved as a mainstream instrument for analyzing dopants. And there are a number of methods that get you close to coming up with the absolute number or what the absolute number would be. But there are too many variables in the approach itself. One of which, it's a contact mode technique, so the tip is resting on the sample and it's scanning back and forth. Well, what's happening is the end of that tip is wearing out slightly as you scan back and forth. So the interaction volume is changing while you're collecting data. So that's one of the things that you have to consider if you were going to try and quantify. The whole procedure for capturing data is changing, and we try and minimize that. We try and minimize those effects. The early days, we used to use metal-coated tips to do this, and the metal-coated tips wore out quickly. So you could conceivably see your signal strength change from the start of an image to the end of an image, okay? And because of things like that, and then the dielectric, I call it an enhanced oxidation. So we grow our own dielectric on that silicon surface, and it's not always the same. Okay, so there may be that may tend to offset your whole data set. So there's so many variables that are convolved into the actual data. It makes it very, very difficult, if not impossible, to quantify. Now, can you approximate? Yeah, but can you come up with an absolute number and say, this area is 5.1 E17? No.
One more over.
Oh.
Very nice data. I haven't polished some stuff. I mean, I know how painful it is. That brings up the question. So nanoprobing is already like at the very end of the failure analysis in terms of localizing, to a few transistors where the defect is, which already is not a method you do all the time because
no.
It's a pain. Nobody wants to do it. Even less than sitting weeks for polishing stuff to get scanning capacitance data. So how often do you really do stuff like that?
This analysis, for example, we did it once. Actually, that's a great question. We're working on sample preparation techniques now. Using a combination of fib and polishing. We're looking into low voltage ion milling, whereby we can use focused ion beam, down to 5 keV to do a cleanup on the surface, and then we'll go in and then do a low voltage ion mill, And I've already kind of worked out, what the details are, what the threshold is that we need to be below in order to not have a deep amorphous layer, something that makes our signal go away. So the process by which we got this data is certainly not something you can do on a regular basis, but essentially what this shows is that the technique, scanning capacitance microscopy and scanning capacitance spectroscopy, can be used on 14 nanometer devices. So right now the only thing holding us back from this being a mainstream analytical technique is just refining the sample prep process. And right now my group is going down 4 different paths and we're pretty close to having a nice, timely, repeatable, robust process for prepping samples. Yep. Oh, I think, yeah. I mean, if there's other questions, I'm certainly glad to speak with you afterwards.
Yeah, in an effort to keep you guys all happy and fed, I'm going to break for lunch here, and that will slide Dr. Baker back to about 1:30, but don't worry, that won't push our reception back too late because we have a little time built into the afternoon to accommodate for this. So please enjoy out in the atrium. Thank you.